Hi, I'm Borna, your organic chemistry tutor, and for this video we're going to be talking about electrophilic aromatic substitution reactions. Now, this is a broad term used to describe a variety of different kinds of reactions, but all those reactions have a lot of things in common. That's why I decided to make this video, and I hope that by the end of this video you can determine what an electrophilic aromatic substitution is, what is going on in there, what the mechanism is, and what affects the rate of these kind of reactions. Let's get started. So in this video, we're going to be talking about electrophilic aromatic substitution. We're going to be talking about what that is, what the mechanism of that kind of a reaction looks like, and some general aspects of electrophilic aromatic substitution we're going to talk about. Alright, so first of all, what is electrophilic aromatic substitution? Okay, so it takes place on an aromatic compound, hence electrophilic aromatic substitution. This is an aromatic compound. It is a substitution reaction, meaning a hydrogen on our aromatic compound gets substituted for an electrophile, and it's electrophilic, meaning that it's generated or it's initiated with an electrophile. Now, how does this kind of a reaction work? Well, aromatic compounds are full of electrons. They have a ring full of pi electrons. And thus, they are nucleophiles. They have a tendency to want to react with things that have electron deficiency. Nucleophiles. Electrophiles, on the other hand, have electron deficiency. And thus want to react with nucleophiles. Now let's look at what that reaction actually would look like with a very simple electrophile. We're just going to call that E+ on benzene. So the way the reaction works is that benzene is going to attack the electrophile is going to add on to our benzene ring, give us an intermediate that is going to look like this, and then in a second step, just move this over, a base of some sort is going to abstract this hydrogen, regenerate aromaticity. Okay. So this is a fast step because the aromaticity is reestablished in this step. There's not much hurdle. But in the first step where the electrophile is being added, you're disrupting the aromaticity, so this is the rate determining step of the reaction. Also, we call this a sigma complex, or intermediate, and it has several resonance structures. And the stability of these resonance structures oftentimes affects how well a reaction is going to go and how fast it is going to react, etc. So on and so forth. Now, what is an actual example of an electrophilic aromatic substitution? An example of an electrophilic aromatic substitution is, say, for instance, nitration of benzene, where you react with HNO3 and H2SO4 to form nitrobenzene, react with, say, Br2 in presence of FeBr3 to form bromobenzene. You react, say, with acetyl chloride in presence of AlCl3 to do a Friedel-Crafts acylation, and so on and so forth. And these are all different kinds of electrophilic aromatic substitution, examples of electrophilic aromatic substitution. Now, these reactions differ in two things. They differ in the identity of the electrophile and how it's generated. Now, let's look at a typical electrophilic aromatic substitution in more depth. Let's look at nitration. When you're doing nitration, say on benzene, for instance, for simplicity, you take benzene, you react it with a mixture of sulfuric acid and nitric acid, and one of the hydrogens gets replaced with an NO2 group. Now, how does that reaction work? Well, sulfuric acid is a very strong acid, even strong enough to donate a hydrogen to nitric acid. So what sulfuric acid will do is that it'll O3H donate a hydrogen to this oxygen of nitric acid, converting this OH into a pretty decent leaving group. So first step, you're going to create something that'll look like this, and then this is going to lose water through this oxygen, forming a double bond with the nitrogen, kicking water out to form NO2+. Now, this is our electrophile, and this is how it's generated. But how it's generated really doesn't affect the mechanism of the reaction. From this point on, the general mechanism that we talked about is going to be basically responsible for what is going to happen. So we have our benzene. Our benzene is going to attack the electrophile. Actually, let's add it to this carbon. It's going to give rise to the sigma complex. And then a base, anything, like this is the fast step of the reaction, so the identity of the base doesn't really matter. I'm writing HSO3- because it gets regenerated this way, and we demonstrate how it's acting as a catalyst, but it's going to abstract that hydrogen anyway to create the final product of the reaction. Now, as you can say, I'm going to talk about one last thing before we close. As you can probably see, electrophilic aromatic substitution reaction involves an electrophile reacting with an aromatic ring. Now, our aromatic ring is acting as a nucleophile here, so the more electron rich, the better. And by the better, I mean the reaction is going to be faster. Now, for instance, if you're comparing this versus, let me just put a strong electron withdrawing group on it, like CF3 in the same reaction, say like nitration, so H2SO4 and HNO3, H2SO4 and HNO3, this is going to be faster because it doesn't have the electron withdrawing group CF3 that exists on the other compound, and that is actually going to slow the reaction down considerably, even to a point where certain electrophilic aromatic substitution reactions may not be feasible with a certain aromatic compound because it's too electron poor. Well, I really hope you liked this video. If you did, please consider subscribing to my channel to see more tips and tricks, solve problems, tutorials, and check out my website at yourokimtutor.com, and share this video and like, and I said subscribe to my channel, I think, but it's not gonna hurt. Subscribe to my channel, I'll say it again, and I'll see you in the next video. Take care.